From this video onwards, we start discussion of chapter 7, which discusses the three very important concepts: inner product, norm, and orthogonality. Now, as is usual with Rao Bhim Chap7, the topic is presented in a garbled way, with lots of unnecessary things coming before the important things. So, what I shall do first is give the basic overview of the topic irrespective of Rao Bhim Chap7. So, these are the things that you should remember, and everything else of use will follow from this. So, having such a basic knowledge will help in order to go through the rubbish presented in the book. Now, one fundamental concept that we use in R2 or R3 is that of two vectors being perpendicular. Now, if I take two vectors that are perpendicular and I want to write down the mathematical condition or the algebraic condition which guarantees this, it is not difficult to see that the condition turns out to be u1 v1 plus u2 v2 equal to 0 in case of R2. Similarly, the condition here turns out to be u1 v1 plus u2 v2 plus u3 v3 equal to 0. From this, it is not very difficult to generalize it to arbitrary Rn. There, if we have two vectors u1 to un and v1 to vn, then we can say that they are mutually perpendicular if this condition holds. Now, of course, this picture does not make any sense there because it is in high dimension. What do I mean by saying that these two vectors are actually perpendicular? But still, I can use this as my definition, though a priori it may not be at all apparent why this generalization should make sense. So, what is this trying to capture? You can always create a definition by following pattern, but what does this mean, or does it mean anything at all? In order to understand that, we will go into another related concept for R2 and R3, namely the concept of length. If we take a vector in R2 or R3, then we can talk about its length. And just as we can capture the concept of perpendicularity using some algebraic expression, we can do so for length too. So, this is the origin and this tip is u1, u2. This is the origin, this tip is u1, u2, u3. In that case, the length of this will be square root of u1 square plus u2 square, and similarly the length in this case, by mistake I wrote R2. In this case, it will be square root of u1 square plus u2 square plus u3 square. We can again generalize this in a brainless way to Rn. If I have any vector u1 to un in Rn, then I can define its length as summation of ui squared and then square root over that. So, we have got two brainless generalizations. One was perpendicularity, summation ui vi is equal to 0. I defined that with the definition of perpendicular, and similarly the definition of length. And the way I presented it, these are just brainless generalization. We do not know what they are really supposed to mean because we cannot visualize them in any geometric way. Now, quite surprisingly, these two things do make sense, and that will come in the form of a theorem. The Pythagoras Theorem, to be precise. Now, we have learned Pythagoras Theorem when we are in school, but we may not have observed that this is the fundamental relation from which all other properties of length and angle takes root. This is the form of Pythagoras Theorem that we learn at school. We start with the right angle triangle. This could be in R3 or R2. So, even if it is in R3, because the triangle is always a plane object, so you can always think of it as if it is drawn on a piece of paper, except that that piece of paper is held possibly in some oblique way in the space. Then the relationship is a squared plus b squared must be equal to c squared. So, what's the big deal about it? The big deal about it is that it gives you the most important concept about distance that we use in our everyday life. Namely, suppose you are standing here and this is a safety zone. So you are unsafe here, there's a tiger roaming, and if you can somehow reach this line, then you are saved. Then how would you run? Will you run like this? Will you run like this? Well, we all know, even a child knows instinctively that we have to run in a direction perpendicular to it. That is the shortest distance. How do you know that that is the shortest distance? The perpendicular is the shortest distance? That comes from precisely this theorem. It says that if you run along any other line, of course, if you run along a curved line, then that will definitely take more distance than going from the same starting point to the same end point in a straight line. So you have to compare only straight line distances. Now this is always greater than or equal to this. That comes from this relationship, and it will c square will be equal to a square only when b square equal to 0. So the perpendicular is the unique minimizer of the distance, and it is from this that all other properties of length and angles follow. In terms of vectors, we can think of Pythagoras theorem like this. You have a vector u, follow it up with another vector v which is perpendicular. I am working in R2 or R3. So in that case you have this vector u plus v, the triangle rule of addition. Now Pythagoras theorem should say that if u and v are mutually perpendicular, in that case length square of this is length square of this plus length square of this. So I should have length square. Let me introduce a notation. By this I will mean the length of a vector, two vertical bars on either side. So this should be this, then u squared plus v squared. And that is this. So if u is perpendicular to v, then length square of this must be length square of this plus length square of this. That is the form of Pythagoras theorem in vector notation in R2 or R3. And as I said, this is the fundamental thing for all our geometric intuition. So if we can generalize this thing to arbitrary Rn, then we have generalized all our intuitions as well to Rn. Now we already had a choice about this. To generalize this in Rn, namely, we said that this will be the case if summation ui vi is equal to 0, and similarly we had generalized this. The question is, if we use these generalizations, will this Pythagoras theorem still hold? And the answer is yes, and the proof is just one line of argument. It is much easier to prove it in general than it was in our early school days. So the generalized Pythagoras theorem takes this form: if u, v are in Rn and if they are mutually perpendicular, then the norm square of u plus v equals norm square. Norm square means the square of the length. So I just use the term norm to mean length, because we do not really want to say length in case of a dimension higher than 3. So we use the term norm, and similarly we do not want to usually use the term 90 degrees. We call it orthogonal when we want to say that they are having a 90-degree angle between them. So if u and v are orthogonal, then norm square of u plus v is equal to norm square of u plus norm square of v, and the proof goes like this. Just a plus b whole square formula is ui square vi square 2 ui vi. This being 0, this sum being 0, you immediately get this. Nothing can be simpler than the proof of the generalized Pythagoras theorem, and this says that if I define orthogonality using this condition, and if I define squared length, squared norm using this condition, then these two definitions play well with each other, and the generalized version of Pythagoras theorem holds. So all our standard intuitions about length and angle hold for arbitrary Rn as well, and that is a great achievement. So I can say if I take a point and here is some subspace of some arbitrary dimension and I want to find that point on this thing which is closest, I can use my familiar R3 intuition or R2 intuition to say it must be the foot of the perpendicular, where perpendicular is to be interpreted in this sense and this distance is to be interpreted in that sense. So for Rn, we have these two definitions. U dot V is summation U by Vi, our familiar definition of dot product. Similarly, norm is square root of this. Observe that I have defined it in terms of the dot product because summation Uy square is nothing but U dot U, and I have taken square root of that. Now, this is for the vector space Rn. There are various other vector spaces which are like Rn, and we can mimic this definition for those vector spaces as well. For example, consider the vector space of all polynomials of degree less than or equal to 4. I also include the zero polynomial, else I will not get the vector space. I am writing it separately because some people say that the zero polynomial has no concept of degree is undefined, while others more correctly say that the degree of the zero polynomial should be minus infinity, which is anyway less than 4. Anyway, so I have to include the zero polynomial. Now, any such entity will be of this form. I am working over field R, so it should be a0 plus a1x plus a2x square, etc. Now, here I can easily see that this is nothing but R5. Other than these unnecessary plus signs and the symbol x, basically this entire polynomial is represented by these 5 numbers a0 to a4. So, if someone gives me two polynomials, I can just treat them as two entries of R5 and talk about the dot product between two polynomials as just a0 b0 plus a1 b1 plus etc. And similarly, I can define the norm square or the norm of a polynomial. Now, notice carefully how you move from P4, which is the vector space of all polynomials of degree less than or equal to 4, to R5. We say basically they are the same things. If I add two polynomials, in that case I will add them coefficient by coefficient. So this is same as adding things here. If I multiply this polynomial by say 2, then I will multiply them coefficient by coefficient, and similarly if I multiply this vector by 2, I will do the same thing. So basically P4 and R5 are the same thing. But of course the way I am writing them, they are different. Now, this moving from this to this is actually affected by choosing a basis. Now, this is not very difficult, but when you hear it for the first time, it sounds confusing. From going from P4 to R5, you are actually choosing a basis, which in this case is 1, x, x squared, x cubed, x to the power 4. So, given any polynomial px, you can express it uniquely as a linear combination of these things, and that is precisely what I have done. So, if you just collect all your coefficients of this basis, then you are getting this vector. So, from a vector space, you can go to corresponding Rn by fixing a basis and expressing every vector in terms of that basis. So here is the general prescription. Suppose V is a vector space of dimension n over R, then I will fix any basis b1 to bn of V. Now if you take any vector V, I can express it as a linear combination of bi's because these are bases, so xi's are uniquely determined by V. So V is basically identified completely using the n tuple x1 to xn. This establishes what is called an isomorphism this term is not very important at this point, isomorphism between V and Rn. So you can think of V as nothing but Rn. So if I take two vectors and add them, their corresponding n tuples get added up. If you take a vector and multiply it with say 5, then its corresponding n tuple also gets multiplied by 5. So whenever you have a vector space of dimension n over R, it is effectively nothing but Rn, and to get this you have to fix some particular basis. So I can generalize the concept of dot product and norm to any arbitrary vector space of dimension n in the following way. I have a vector space over R of dimension n. I take any two vectors in V and I want to define their dot product. How do I do it? I first start by fixing a basis. Then these vectors u and v become just n tuples with respect to that basis, like this. So u is basically same as x1 comma dot 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 up to xn, which means x1 times the first basis vector, x2 times the second basis vector, etc. Similarly for v. And now you can very easily define this thing as summation ui vi, much like the way we did earlier. And we can similarly extend the concept of norm precisely the way we did in terms of this dot product itself. So I will define it as square root of u dot u. And then whatever intuition we had about our distance and angles, etc., they all work because Pythagoras theorem holds here also the same proof.